Hello, you are welcome back. All right, so in this video we are going to be discussing magnetic circuits. All right, so what is a magnetic circuit? A magnetic circuit is simply a closed path through which magnetic flux is established. All right, okay, I'm very sure that you're familiar with the magnetic flux of a bar magnet. Okay, now let's start with the magnetic flux of a bar magnet. Every bar magnet will have magnetic flux, okay, and that is known as magnetic line of force, which can be represented by an imaginary line. Okay, for a bar magnet of this nature, okay, we'll have the north pole and we'll have the south pole. Okay, so the flux is established, okay, emanate from the north, then of course terminate at the south. Now it's a circuit because it's a closed path. Now though it is not seen, there's another flux that actually moves from the south. Okay, it is closed, so it's from the south back to the north. So it's a closed circuit actually, but you can't see the one because it's that flux is taking place. All right, that flux is established inside the bar magnet. So anytime you have a closed path like this through which magnetic flux is established, okay, then that is a magnetic circuit. Now apart from the magnetic circuit that is established by a bar magnet, because this right here already there's a pole, the north pole and the south pole, already is a bar magnet. Now we can actually have that in an electromagnetic uh, uh, electromagnetic circuit, okay, where you have a coil of wire wound around a core. Now this is a magnetic, all right, core. Okay, please pardon me. So this right here is a core. All right, now this is a coil of wire, and this coil of wire is being supplied with current via this voltage source. All right, so the current flows through the coil. Now as the current flows through the coil, you will notice that the flow of current through the coil actually establishes magnetic flux, and of course that magnetic flux follows this path. All right, okay, from the north pole, because now you are supplying, all right, a current to this coil, right? So the coil now becomes a bar magnet. One end of the coil is the north, while the other end becomes the south, and as a result magnetic flux is established, which follows through a path and return back to where it is actually coming from. So it is a closed path. All right, so please take note of that. Okay, so now let's look at the basic terms and formula, right? So basic terms that we need, right, to know. The very first term is important. I'm very sure that you know this already. Is a magnetic flux. Okay, we talked about this. So this is magnetic flux. Now magnetic flux is actually the total number of line of force. So the symbol is phi. Okay, so total number of line of force. Total number of line of force that is established in the magnetic circuit, all right, is the magnetic flux, and the SI unit is Weber. All right, the SI unit is Weber, abbreviated as WB. So please take note of this. Okay, so this is, I just only used one imaginary line to just show just one line of force, but there are many of it, and the number of line of force actually depend on the intensity of the magnetism that is established, and the intensity of the magnetism that is established depend on the amount of current. Okay, depends on the amount of current that is supplied to the coil. I hope that is well understood. All right, so number 2. Okay. Number 2, let's look at magnetic flux density. Okay, here we're going to talk about magnetic flux density. Yeah, I'm sure you know this already. The symbol is B. This is defined as magnetic flux per unit area. Magnetic flux per unit area. Okay, so the SI unit for this, okay, is equal to, of course, that should be flux is measured in Weber, area is measured in meter square. So 1 Weber per meter square is equal to 1 Tesla. I'm very sure you know this already. Okay, so please take note of this. Okay, so the third basic concept we're going to discuss is known as the magnetomotive force. Magnetomotive force. Now, this is actually analogous, okay, to electromotive force you have in electric circuit. So the symbol is MMF. All right, so of course, this is actually the force that actually establishes flux in a magnetic circuit. Remember, something must drive or must cause the establishment of flux in a magnetic circuit, and that is the magnetomotive force. Without the magnetomotive force, all right, there won't be any flux. And of course, the magnetomotive force is based on the current. A situation where let's say you open the circuit, all right, then definitely there won't be any flux established in this magnetic circuit. So what actually causes the flux to be established is the current that is supplied to the coil. So now, magnetomotive force, MMF, is proportional. Okay, let me just put it this way. Is proportional to the current that is supplied to the coil. And of course, if I remove this proportionality, I'll bring a constant. So the constant is simply the number of turns, all right? Number of turns of the coil. So please take note of this. So this is the magnetomotive force which establishes magnetic flux in a magnetic circuit. Now, it happens that this magnetomotive force, all right, is the work that is done. It is work that is done. And by the way, the SI unit of this, the SI unit of current is ampere. The SI unit of number of turns, you can just call it turns, all right? So you can just use the SI unit is ampere turns. Ampere for current, turns is for the number of turns of the coil. All right. Now, you should also take note of this. Magnetomotive force, okay, is calculated as the magnetizing force times the length of the conductor. So the length of the coil or the conductor, okay? So this is another formula you should take note of. Okay, because magnetomotive force is actually given as the work that is done in moving or in establishing a flux. So because I won't say moving a flux is not like current that moves, okay, but flux is being established. So the work that is done in establishing a flux around a magnetic circuit is magnetomotive force. And you know that work, all right, work is equal to force times distance. So in this case, in the case of magnetism, the force is magnetizing force, which is H, and the distance is actually the length of the conductor. Okay, the length of the distance is actually the length of the flux, not the length of the conductor. Please pardon me. Okay, like in this case now, let's go to that particular magnetic circuit that we have. So as you can see, the length of the flux is actually the circumference of the circle. Okay, this is a circle. The flux is circular in nature, so the length of the flux is going to be simply the length or the circumference of the circle, which is giving us a 2 pi r. Okay, and r is simply the radius of the circle, so please take note of that. So depending on the shape of the flux, all right, uh depending on the shape of the flux, okay, we need to calculate the length of the flux for us to be able to evaluate the mmf. So mmf is given as hl. Okay, then of course it's equal to ni. So and from here now, okay, it is very much easy for you to calculate magnetizing force. So this h represents magnetizing force or magnetic field strength. Okay, it is also the same as magnetic field strength. Okay, so the SI unit, the SI unit of magnetic field strength is magnetic force per unit per okay per unit pole. Magnetizing force or magnetic field strength is magnetic force Newton, okay, then per unit pole. A pole, right, the strength of one pole is measured in Weber. It's measured in Weber, okay, so Newton per Weber. Of course, there are other units. I'll still introduce other units to this, but this is really very important. Okay, all right, but I can actually get this is the 1 unit. Then the unit can also be okay be gotten from what we have here. So this is h. If I make h the subject of formula, the magnetizing force can be equal to the magnetomotive force then divided by the length of the conductor. Magnetomotive force is measured in ampere-turn and length of the conductor is measured in meter. So ampere-turn per meter is another unit, all right, for magnetizing force. So these are really very important. So these few formula are really important because we are going to be solving some question. Okay, so here we go. Let's start with the very first question, if I have it. Okay, I hope I will. Yes, problem 1. So let me shift this a bit. Abrasti, let me begin. Okay, solution. Okay, so let me read the question. It goes this way: a magnetic pole okay, has a rectangular section having dimensions of 200 meter by 100 meter. Okay, so that simply means that the area is gonna be of course this is a rectangle. Okay, please pardon me, let me okay. Okay, let me have let me solve another one. I'm having issues with this one. Let me work on this. Okay, I'll return back to that. All right, so okay, this problem 2. Let me solve problem 2. The maximum working flux density of a lifting magnet is 1.8 Tesla. All right, so that simply means that Um, flux density B, according to the question, is 1.8 Tesla. The area, as a matter of fact, has been given. So, and the effective area of the pole faces is a circular cross section. So, it's circular cross section. Okay. So we don't know the area. If the total magnetic flux is, we don't know the area. Let me put that as a question mark. The total magnetic flux phi, according to the question, is 353 milliweber. Okay. So what are we looking for? We are looking for the radius. Okay, the radius of the pole. So we cannot evaluate the radius of the pole without evaluating the. We have to get the area first. So how do we get the area? So we apply the formula. Magnetic flux density is equal to magnetic flux all over area. Okay, so magnetic flux density that was given is 1.8. Is equal to magnetic flux, which is 353. Then of course milliweber. So I have to convert that. Milli is times 10 raised power minus 3. Then divided by the area. That's what I'm looking for, the area. So from here now, if I divide this 353 by 1000, okay, then of course I will have 0.353. So area is going to be equal to 0.353. Okay, 0.353 then divided by 1.8. Okay, so let me get a calculator to help me work on this. Okay, so I hope. All right, so here we go. So with what I have, all I'm doing now is I'm dividing. So what I do, I have to divide 0. Okay, here we go. So I'm dividing 0.353. 0.353. Okay, divided by 1.8. What do I have? Okay, 0.196. So this is 0.196, and of course it's in meter. Okay, so here we go. So with this now, area, remember that is a circular, right? It has a circular cross section. The area of a circle is pi r square. Okay, so that means if I make radius the subject, that's going to be equal to the square root of area divided by pi. Okay, so here we go. So this is going to be the square root of the area, which is 0.196 divided by pi, which is 3.14. Okay, so here we go. So let's divide that. Okay. Okay, so here we go. Divide by 3.14. Divide by 3.14. Okay, 0.062. So find the square root of 0.062. Let's do that. 0.24 approximately. So the radius is 0.24 meter. I hope that is well understood. Okay, let's look at another question. Okay, so let me clean up all this. I don't need it. Okay, so here we go. Let's work on this. Okay, here we go. Now this one goes this way, a core of 300 tons. So solution, let me write the parameters. So I have to write the parameters, okay? So the number of tons of the core is 300. 300 tons. All right, is wound uniformly on a ring of a non-magnetic material. The ring has the mean circumference of 40 cm. The circumference of the ring is 40 cm. Okay, so that simply means that the length of the magnetic flux is 40 cm. So, of course, we have to convert that to meter. That will be 0.4 meter. Okay, so here we go. And the uniform cross-sectional area of 4 centimeters square. Okay, so this is in cm. This is also in cm. Okay, let me still convert this to meter. Of course, to convert this to meter, you are dividing by, okay, 100, then square. I'm converting it to meter square, okay? So that will be 4 times 10 raised to the power of minus 4 meter square. Okay, so what are we looking for? If the current is 5 ampere, the current supplied is 5 ampere. So what are we looking for now? The magnetic field strength, that is, we're looking for H. Okay, so we are looking for H, that is the A part of the question. B part of the question, we are looking for B, magnetic flux density, and we are also looking for phi. Okay, so let's start with the very first. Okay, so let's start with H. Of course, you know very well that MMF is equal to HL. Okay. Now, so MMF is equal to HL. Since we are looking for H, and we know that HL is equal to, being the MMF, MS is equal to the number of turns multiplied by current. Okay. So they are equal, right? So H, as a matter of fact, will be the number of turns times current divided by the length. Okay, so here we go. Number of turns is 300. Then multiply by the current, which is given as 5 ampere. Then all over the length. Okay, that's 0.4. Okay, so here we go. Okay, pardon me, let me. Okay, here we go. So, of course, this is going to be equal to 1,500 if I'm not mistaken. Okay, so this is 1,500 divided by 0.4. All right, so 3,750. Okay, so this is 3,750 ampere ton, okay, per meter. So we've gotten that. This is the A part of the question. We've gotten the answer. Then the B part of the question, we are looking for magnetic flux density, which of course is magnetic flux all over area. Okay. Yeah, now we can't use this formula because magnetic flux is not given. Okay, but rather the formula we are going to use is the one that relates magnetic flux with magnetizing force. Please take note of this formula. I really hope I gave you the formula, but if I don't, just write it down somewhere. Okay, so please take note of this. The relationship that exists between magnetic flux density and magnetizing forces. Magnetic flux density is equal to permeability of the medium, then multiply by the magnetizing force. So that is the relationship. So this is what you're going to use if you want to calculate magnetic flux density from the magnetizing force. So now in this case, the material, okay, this is a non-magnetic material. So since it's a non-magnetic material, so we can definitely have it that the relative permeability is 1. Okay, and don't forget that permeability, okay, let me go to the next slide. Permeability of a magnetic material is given as the relative permeability then multiplied by the absolute permeability. Okay, so in this case, this is a non-magnetic material, so the relative permeability will simply be 1. So we have it that B now is going to be equal to 1 times absolute permeability is the absolute permeability then multiplied by H. And you know that absolute permeability is a constant, okay, has a constant value of 4 pi times 10 raised to the power minus 7, okay, then multiply by the H that we've already calculated, which is 3750. Okay, so let's do this. So I can work on this 4 pi. So let's work on that. 4 pi, this pi is 3.14. All right, so then of course times 3750. Okay, then I've divided by 10 raised to the power of 7. Okay, because 10 raised to the power minus 7 is the same as 1 all over 10 raised to the power 7. So divided by 1000000 then 0. Okay, here we go. So that's 0.00471. Or put it in a standard form. Okay, 4.7 times 10 raised to the power minus 4.7 times 10 raised to the power of minus 3, and is measured in Tesla. All right, so I hope that is well understood. Then finally, the last but not the least, the flux. C. So to calculate the flux, we use the formula magnetic flux density is equal to flux all over area. So if I cross multiply, all right, then definitely flux will be equal to B multiplied by A. So magnetic flux, okay, is 4.7 times 10 raised to the power minus 3 times the area. Okay, so of course, how do we calculate the area is 4 cm, which of course is 4 times 10 raised to the power minus 4. So 4 times 10 raised to the power minus 4. So here we go. The magnetic flux now is it's now being calculated as, okay, 4.7 then times 4, 18.8. So here I have this is going to be 18.8 times 10 raised to the power of minus 7. Okay, and that will be in Weber, or you can still put it in a standard form. That is 1.88 times 10 raised to the power minus 8 in Weber. Okay, so that is it. That is it for this video. We are going to look at more in the next video. See you in the next video. Thank you very much.